Our next speaker is Ali Haydar. Ali he's a civil engineer with a PhD and a strong background in structural analysis, finite elements, and thermal modeling. Do you want to join me on stage, Ali?
Thank you.
And today is going to talk to us about a flux-based finite element analysis for thermal analysis, of laminated glass facades with cast shadows. Let's give him a round of applause. Thank you.
Hello, thank you. Just need the device for changing.
I think Barbara stole it. Not she didn't. It's here.
Thank you. Hello, everybody. I'm Ali. I'm from University of Parma, and we did a research about flux-based finite element analysis for the thermal analysis of laminated glass. Of course, this laminated glass is subject to shadow. The work has been done in collaboration between Mafface Engineering and University of Parma. The speaker before me talked about the thermal cracks caused by shadows, by other kind of thermal stresses, and we here present some kind of important problem in facade design. Additionally, any kind of facade can be subject to cast shadows that can vary in shape, in form, and timing. So here we can see some small examples about it. Mainly, what I want to talk about is the difficulties in the thermal analysis of these structures. What we have in case of laminated glass, a connection between two different materials that are the glass and the PVB, which has different thermal properties. At this interface, we have non-smooth temperature fields, and also at the interface between the shaded area and the unshaded area. The boundary conditions of this problem are usually radiation and convection. Additionally, when we are studying the IGUs, we have the phenomena of multiple reflections and nonlinear absorption of solar radiation. Traditionally, the study of the thermal problem is based on the scalar field of temperature. And a novel approach was suggested by Biot in 1955 based on defining the heat displacement field, as we can see here. The difference between the two approaches from the first point is the temperature is a scalar field while the heat displacement field is a vector field. Another point of difference, the boundary conditions of the normal problem that we face in reality are conditions on flux. And to enforce them using a finite element model in the traditional approach, we need higher continuity for interpolation. This is the opposite case in the vector field approach, where the linear interpolation is sufficient. The irregularity of the heat displacement, the temperature field at the contact surface between different materials like glass and PVB causes some kind of problems in the numerical analysis, while the heat displacement field is always continuous. Additionally, the most important law in studying this kind of problem is conservation of energy, which is enforced indirectly in the traditional approach, while it is a holonomic constraint in the novel approach. This approach was suggested by Maurice Biot in the 1955, but when he formulated his variational principle, he followed the mixed formulation, where the temperature and the heat displacement field are getting approximated. The traditional flow approach has difficulties also in modeling non-smooth heating conditions like I talked about it, the casted shadows. While non-smooth heating conditions in the vector field approach are easy to model because the heat displacement field is always well behaved. As I said, Biot did a mixed formulation where the temperature and heat displacement field are approximated, but in our case, the novel neat flux-based variation principle is formulated in terms of the heat displacement field only, while the temperature only appears on the boundary. And that's why we call it the neat. Here I'm not gonna go into detail for the mathematical formulation, but we can check that temperature only appears on the boundary when assigned, and we have the H sharp, which is the heat displacement field that represents solar radiation and generation of energy inside the body, while theta 0 represents the initial temperature of the structures. We formulated a variation. The variation principle allows us to formulate very simple finite element, which we can use the standard hex 8 finite element, and we can get the discretized equations as you can see. While after calculating the heat displacement field, we can get the temperature field a posteriori using the Fourier law. The boundary conditions of this problem are prescribed temperature at the boundary, which is a contact with a heat reservoir, while prescribed heat flux at the boundary is enforced by the normal the normal component of the heat flux. And when Q is equal to 0, we have the isolated boundary. The Rubin condition can be used to represent radiation or convection, some cases linearized radiation. Here I'm going to present some data to represent the problem that we have dealt with. We are dealing with a partially laminated glass plate, where the shaded area we are considering that is taking 10% of the solar radiation. And the external environmental temperatures are a function of time, also the solar radiation. And we consider the winter scenario. The boundary conditions are conduction, convection, and radiation. Here we consider this problem, where the square shadow on the left downside is shaded, and the plate is laminated. Doing the thermal analysis using the finite element I described, we can get these results. And if one would implement the original approach that was suggested by Biot, you can get some singularities at the corner of the shadow. While the new flux-based formulation does not face any kind of these problems. I will present another example related to variable shadows. As we can know, when the sun is moving in the sky, the size of the shadow can change, and consequently, the heat distribution in the plate will change. Here we consider a variable, different cases of this kind of shadow, and we present the most important thing, that is the difference in temperature between the shaded area and the unshaded area is not affected by the size of shadow unless the shadow is very small or very big, where the transition area, that is a sigmoidal curve, does not have enough space to develop. Additionally, we did some parametric analysis to study the relationship between the width of transition area, transition strip, and the thickness of the plate. And we can see there is a functionality between the width of the transition strip and the thickness of the plate. Of course, we can study the effect of shadow shapes. And we can see here, for example, this is considering a plate that have a frame on its boundary. And we can see that the difference in temperature between the shaded and irradiated areas is not really affected by the shape of the shadow. But in case of a stress analysis, of course, at the corners or any kind of concentration of temperature, there will be a stress concentration. Another example that we have dealt with to demonstrate the efficacy of the model, we have the ISS space station window that is 800 millimeter. And this glass window that is subject to extreme environmental conditions has the partial shading due to the supporting frame, and it has a cyclic exposure to the solar radiation because of the rotation around Earth. The cycle of exposure is 90 minutes. We can see here, using our model, we are able to model the change in temperature when the space station passes between the sun and the eclipse region. The same problem of the window is its composition. And usually the space station window is composed of multiple layers that are separated by vacuum. And as I said, it's subject to the shadow of the frame and the shadow caused by the rotation around Earth. But also, as you can see here, what do? We can exploit the symmetry of loading conditions to model only part of the structure. Also, you can call it the Italy transformation. If you have a pizza, you change it to a triangle, and then you eat it. So we can see here we did a composition of fused silica, and acrylic glass. Fused silica does not absorb solar radiation, but as you can see, everything of the increase of temperature due to solar radiation is happening in the third layer, which is made of acrylic glass. Nonetheless, the acrylic glass is able to heat up the fused silica because of the Stephen-Boltzmann law and interaction of radiation. Okay. The model that we have suggested is very general to the degree that we can also model discontinuous temperature field that can happen at the interface between different materials. This condition is where the flux on the boundary between the interfaces is a function of the difference in temperature. The efficacy of the model is being able to solve such problem in the traditional approach requires a huge number of finite elements. In this particular example, the original research that we compared with needed almost 500 elements per layer. In our case, we only need 5 elements per layer. I will explain the small contribution that we did. We have suggested a novel need variational principle built on the heat displacement field suggested by Biot. The finite element implementation is very simple and effective. We are able to do advanced analysis of laminated plates and IGUs. We also are able to incorporate nonlinear radiation laws. And of course, if you are interested in this topic, please send us an email to Maface Engineering. And thank you for your attention.